Welcome everyone. Welcome to the digital communication session. In lecture 6, we will continue the last topic, line coding techniques. In line coding techniques, we have done this. We will convert a digital data into digital signal. So this is the digital data. We are converting this into digital signal. In the previous lecture, we have done so many line coding techniques, that is unipolar, polar, Manchester, differential Manchester. I am just recalling the line coding. What will line coding do? Line coding which convert over binary data into digital signal. Like 0 will be represented as a 0 voltage, 1 will be represented as a 1, and 0 will be represented as a 0 voltage. That will depend upon the which type of line coding technique we are using. Here we are representing 0 as a 0, 1 with a 1 volt and 0 as a 0 volt. Now next type of line coding techniques, that is bipolar. In last lecture we have done unipolar, polar and Manchester. Now next is bipolar AMI. Now what is AMI? AMI is known as your alternate mark inversion. In this term alternate mark inversion, the word mark comes from the telegraphy, which means 1. So AMI means alternate 1 inversion. Whenever the 1 will come, we will invert the voltage alternately. A neutral 0 voltage will be represented binary 0. Binary ones represented by the alternating positive and negative voltages. A variation of AMI encoding is called a pseudo-unitary, in which the 1 bit is encoded as a 0 voltage and 0 bit is encoded as a alternating positive and negative voltage. Is the reversal of this AMI pseudo-unitary, in which 0 will be represented as a alternate voltage changes and 1 will be represented as a 0 voltage. Now see in this example, here we have data is given 0, 1, 0, 0, 1, 0. Now 0 will be represented as a 0 voltage, 1 will be represented as a positive voltage. Now again 0 is come, it will be represented as a 0, next is 0, now next is 1. Now here alternate mark inversion, when we will have to do the alternate, whenever the 1 is come, the last one is having a polarity positive. Now here we will invert the polarity, it will become negative, right? And for the 0, it again 0. In pseudo-unitary case, 0 will be represented as a positive voltage. Here you can see 0 will be represented as a positive voltage. Now 1 will be represented as a 0 voltage. Now next 0 will come, we have to invert this last polarity, that is positive, it will be negative. Again 0 is coming, it will become positive. For 1 it will be represented as a 0 and 0 again it will be negative. AMI is commonly used for the long distance communication, but it has a synchronization problem. What is the synchronization problem? At the receiver end, where we are receiving the signal, this signal, when a long term of 0 will come, so it will do the synchronization problem, because 0 is represented as a 0 term. Now this later will be overcome by the scrambling techniques. Whenever the long 0 will come, that will be overcome by this scrambling technique. I will give you another example. Now suppose this is our data 101, we have to do the AMI for the same. Now here we will do the AMI RZ. Similarly AMI also has two types, AMI RZ and NRZ. This is the example of NRZ, non-return to 0. As you can see in this, for the complete bit duration we are showing the pulse. For the complete bit duration we are showing the positive voltage. Now first we divide this into 4 parts. First bit is 1, we are doing the AMI RZ. 1 will be represented as a 1 voltage, but due to this RZ it will return to 0. It will show having a value 1 for this half bit duration. Next bit is 0. 0 is represented as a 0 voltage. same in RZ case. Now again 1 will be presented as a, now last voltage is positive, so this voltage will be negative, but for the half duration. It will show the reversal alternate mark of this whenever 1 is come, and 0 will be presented as a 0. So you can see the difference between this and this graph. Here the width of the pulse for the complete bit duration. Here you can see the half bit is required for single representation, that is RZ. It is very much clear what is RZ and NRZ. Now let's proceed to the next slide. Now scrambling. In the previous slide I have told you, when the long sequence of 0 is present, there is a synchronization error that will be overcome by this scrambling process. Scrambling, that is very suitable for the long distance communication because of their wide bandwidth requirement. Now this bipolar AMI encoding has narrow bandwidth and does not create a DC component. However, a long sequence of zeros upset the synchronization. If we can find way to avoid a long sequence of 0 in the original scene, we can use bipolar AMI for long distances. Now in scrambling process we will do the AMI line coding technique, whereas we will just substitute the whenever the long string of 0 will come. We will do the AMI encoding technique only, and just we will replace the long zeros by suitable term. We use modify part of the AMI rule to include the scrambling. We will use the AMI rule in the scrambling process. As shown in the figure, we will do the figure. Now, two common scrambling techniques are B8ZS and HDB3. These are the two type of techniques, B8ZS and HDB3. This two techniques is used to substitute over long zeros of sequence. B8ZS is bipolar with 8-0 substitution. B8ZS means bipolar 8-0 substitution. Whenever long string of 8-0 will come, we will replace data by this term 00V B0VB, whereas V is denoted as the violation and B is denoted as a bipolar. Whenever long 0 will come, that will create a synchronization error, so that will be replaced by this sequence 00V B0VB. Now see in this case how we are doing the, see in this example. Suppose this is our data 1 0 0 0 0 0 0, and you can see this total 0 is 8. When 80 will come, we will replace this data by this 00VB 0VB. Now this can be done by the two method. Previous level is positive and previous level is negative. When we take 1 as a positive voltage, then this 0 0 0 0 0 will be replaced by this term V B. Now this 0 0 0 V will be 0 0 BV 0 0 VB. It will be replaced by the positive pulse and negative pulse, starting pulse. Starting pulse is positive, then this 0 0 0 V B 0 VB will be replaced by 0 0 0 positive negative 0 negative positive. This plus sign for the positive voltage, फिर this means negative voltage 0 minus negative voltage plus. Now see in this example 0 0 0 VB will be replaced by 0 0 plus, means we have to show positive voltage here. Now B0 VB will be shown by the negative 0 negative positive, negative 0 negative positive. When the, always remember, when the level is positive we have to replace by this term, that is 0 0 0 positive negative 0 negative positive, by this kind of pulses. This will be replaced by the long consecutive zeros. 8 times 0 will be there, we have to replace by this term, this polarity. When the previous pulse is positive, when the previous pulse is negative, then long 0 will be replaced by this format. See in this next, see in this, when the previous voltage is negative, then this is will be replaced by 0 0 negative. See 0 0 negative and positive 0 positive negative, positive 0 positive negative, 0 0 0 negative positive 0 positive negative. Always remember this starting pulse is we have taken negative or positive, right, that is our bipolar 8-bit substitution. Next is HDB3, that is high density bipolar, high density bipolar. HDB3 is commonly used in North America in this technique, which is more conservative than BA8ZS. Here we are choosing the 4 consecutive bits level, that is will be replaced by 00V or B00V. In this scheme we are replacing 4 bits of 0 by 000V or B00V. Now the reason for 2 different substitution is to maintain the even number of non-zero pulses. After each substitution the 2 rule can be stated as follow. If the number of non-zero pulses, previous one means which having the voltage, if number of the non-zero pulses after the last substitution is odd, the substitution pattern will be 00V. Suppose we have to do line coding for this data. See 40 will come here, 000. We have to count the previous one here, the previous one here non-zero, that is 11, that is even. If the previous one is even, that will be replaced by B00V. Here we are changing B00V, right. If the previous one non-zero pulses is odd, then substitution pattern will be 00V. This 4 substitution pattern. Now here you can count 1, 2, 3 odd, that will be replaced by 00V, right. Now at this point again 40 will come, you have to count all previous one here non-zero pulses. Now we have to include this BV pulses also, that is 1, 2, 3, 4, 5, 6. Now here the value is 6, 6 is even, so even will be replaced by B00V, B00V. Right. Even once previous one is 0, then it will be replaced by B00V. We have to represent data in this format, plus 00 plus. Odd ones hai, then we have to replace 00V and the voltage will be represented as 00 minus. I will show you an example. This is our data 1 0 1 4 times 0 1 4 times 0. We have to do the HDB3. Now 1 will be represented as a positive, 0 will be represented as a 0, 1 is represented as a negative voltage. Now here you can see 4 number of consecutive 0 that will be replaced by this HDB3. Now previous one we have to count 1, non-zero pulses is 2, even 1 will be replaced by B00V. It will be replaced by B00V. But in during this voltage in this signal line coding technique, we have to do the plus 0 0 plus. We have to do this a sign plus 0 0 and plus. That is over B00V. Now for this next one, here is the last voltage is positive, we will do this negative because it will follow the AMI rule. Now again count 40 will come. Now we have to count the previous pulses, non-zero pulses. Count it 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 pulses is there. When the previous pulse is odd, then it will be replaced by 0 0 V. This 4 times 0 will be replaced by 0 0 0 V. Now but to show in this graph, it will be show 0 0 0 negative, means 4 times 0, 1, 2, 3, 4 and negative voltage. It is over 0 0 0 V. Right? This is the example of HDB3. Now here is the complete compilation of the line coding that we have done. This is the data we are just revising that we have done so far. 1 1 0 1 0 0 1. This is the binary data. In unipolar NRZ, we will show plus voltage, right? Whenever the 1 is come, we will show the plus voltage. Now here you can see this is NRZ for the complete bit duration. For the 0, it will be presented as a 0. 1 plus a 0, 0 and again 1. Right, this is the example of unipolar NRZ. Polar NRZ, 2 voltage will be there. Here we are showing the 1 as a plus voltage, and for the 0, it is doing the negative voltage. Here you can see in unipolar there is no another voltage level, only A will be there. Here A and minus A will be there. 0 will be rendered as a negative voltage. Again 1 positive, 0 negative, negative, positive. Now unipolar RZ, compare this and this. We have to do the 1 voltage level only, plus A, but the bit duration of the pulse is reduced. Only half pulse will be there. For the next one, same, it will be having a plus A, and the next 0 will be rendered as a complete 0, then plus A, complete 0 and plus A. Is the RZ. Bipolar RZ that we have done in today's lecture. Whenever the 1 is there, we have to show the pulse, and for this RZ for the half duration. When the next one is come, we have to do the inversion, alternate marking. यहाँ positive है तो यहाँ पे negative voltage. 0 will be presented as a 0. Again, you can see negative voltage there, and it will be show you positive voltage. Now 0 will be presented as a 0, 0 will be presented as a 0, positive voltage means negative voltage, data will be 1 here, 0, 0. You can also generate the binary data from these pulses, because we know when the plus is there, it means 1 voltage, 1 bit is there. Again alternating means 1 is there, 0 in case of bipolar, 1 0 0 1. Last is Manchester that we have done. In Manchester, 1 is represented as a high to low, and 0 will be represented as a low to high. You can see 1 is represented as a high to low, and again high to low, and here he is starting from the negative level, which means 0 data is here, 0, low to high, high to low, low to high, low to high and high to low. So in this line coding technique, we have done different type of line coding. In these two lecture, we have done unipolar, polar, unipolar, bipolar, and scrambling. Scrambling, that is overcome this bipolar synchronization error. That's it. In next session, we will do the PSD, power spectral density. We will compare unipolar RZ, polar NRZ, and bipolar NRZ. That's it. Thank you, everyone. In next session, we will do PSD.